students, you are welcome to Maths Secret Revealed by Dr. OJ. In this video, we shall consider uniform convergence of sequences of functions. This is a follow-up to what we learned in the pointwise convergence of sequences of functions. But today we want to consider how sequences of functions converge uniformly. Now, let's start our definition. Let's start our definition. Fn, when n is moving from 1 to infinity, be a sequence of functions. Let Fn be a sequence of functions. Now, Fn converges. Fn, that is the sequence, Fn converges uniformly, if for all point x in the domain of the function, there exists a natural number n such that the supremum of x in the domain of our definition, of the absolute value of fn of x minus f of x, tends to 0. And what we simply mean by this, that is, if we pick a number or a point x in the domain of the definition, suppose the domain of our definition is a closed interval 0, 1, okay, and we have fn taking a point, an interval 0, 1 to set of real numbers. Okay, so now if you pick a point x in this domain, then we have the supremum, that is the maximum value of x coming from that domain of the definition of the absolute value of fn of x minus fn must tends to 0. As n tends to infinity. So this means that fn of x converges to f of x. This means that fn of x converges to f of x. And the limit function here is f of x. It is uniformly convergent across the entire domain. And the rate of the convergence does not depend on x. Unlike in the previous definition of pointwise convergence, the rate of convergence, you could observe, was carried out separately. The convergence was carried out separately because that implies that for every x, in that domain, the convergence is different. But in the case of uniform convergence, from the word uniform, it means that if you pick a point x in the domain of that definition, every point picked there will convert to the same value, and that is to say that the convergence is uniform. It does not depend on x. Whether x is x1, x2, whatever, they are all going to convert to the same point. That is what I mean by uniform convergence of sequence of functions. So let's illustrate this definition with a simple example. Let's illustrate this definition with a simple example. Okay? I hope you are listening. I hope you can now see the difference between uniform convergence and pointwise convergence. Now, example 1. Let's look at this example. Let fn of x is equals to x all over n on the interval, that is the domain given to us, is 0, 1. Now for each x, let's say the x is fixed, for each fixed x, in that domain. Now fn of x tends to 0 as n tends to infinity. What do we mean by this? Now we're trying to show that if you pick a point x in that domain, don't forget, picking x in that domain, x could be 0, x could be 1 over 2, it could be 1 over 3, it could be 1. So whatever x you pick in that domain, the function, the real value function, which is going to be the limit function, must be 0. That is, the sequence of function fn of x will definitely converge to 0. And from the supremum, like our definition, we said that the supremum of absolute value of fn of x minus f of x must tend to 0, when x is taken from the domain. So that means that our f of x, which is the limit function, must be 0. So now, to check the uniform convergence, now we have note that the absolute value of fn of x minus 0 is equal to x all over n. What do we mean by this? Looking at that definition, we said the supremum of the absolute value of fn of x minus f of x will tend to 0. And we have given fn of x to be x all over n. That is, I'm saying that the absolute value of x over n, minus 0 will equally be x over n. Are you bothered that I got my 0? You shouldn't be. Because I said in the definition that the absolute value difference between fn of x and f of x must tend to 0, which invariably means f of x, our f of x is 0. That is what it means. So if f of x is 0, that means, fn of x minus 0, which is f of x, is equal to x over n. Another way of looking at this, if suppose we pick 0 as our x, 0 all over n is 0. If you are considering saying that f of x, is tending to 0 and x is 0, that will be 0 over n, which is 0. So fn of absolute value of fn of x minus f of x, which is 0, is equal to x of n. But generally, as a uniform convergence sequence of function, it is always defined this way. Now let's look at the maximum deviation, because the definition says that the supremum of the absolute value. So that means we need the maximum deviation. The point at which the deviation is very, very large. We are given two limit points. Two points. We are given 2 points. We are two endpoints. We are given 2 endpoints. We are given 0. We are given 1. So picking the maximum value of these 2 points, the maximum deviation will come from what? Come from 1. So we can have the maximum deviation. You write. You can say the maximum deviation of this particular problem occurs at x is equal to 1. It occurs at x is equals to 1. Okay, so the supremum of x in 0, 1 will now be absolute value, the absolute value of fn of x minus f of x, which is the same thing as sup x coming from 0, 1, and the absolute value of fn of x, that is what? Fn of x minus 0. That will be equals to 1 over n. Minus 0. Why? How come I got 0? Fine. Because we are picking our x to be equals to 1 here now. If our x equals to 1, and we are saying that the supremum of the absolute value of fn of x minus f of x must tend to 0. Okay? now by definition will be equal to x all over n. So if your x is 1, this one becomes 1 over n. I hope that is taken. And obviously, taking the limit of 1 over n as n tends to 0, you will see that the value we are going to obtain is 0. Okay? So as n tends to infinity, the supremum of the function tends to 0. So the supremum tends to 0, hence, you know, fn of x, hence fn of x tends to 0 as n tends to infinity. So this is a very, very good example of uniform convergence of sequences of function. So you could see the difference between uniform convergence of sequences of functions and pointwise convergence of sequence of function. So try as much as possible to understand the difference. The basic difference is just that in uniform convergence of sequence of functions, our convergence does not depend on x. Whether x is whatever within that domain, the result, the limits we are going to obtain for all the points within that domain is going to be the same. But in the case of pointwise convergence, we are going to obtain different values for the limits at a fixed point x in that domain. So with this, we have come to the end of uniform convergence of sequence of functions for now. In the next video, we will elaborate more with possibly theorems to establish the concept of uniform convergence of sequence of functions. Don't forget, click on the notification bell so that each time I upload a video, you'll be daily notified. God bless you.